Injection Worldwide Limited is a British-based company, and we sell two technologies. The first technology is gas-assisted moulding, which is now more than 25 years young. We've been selling it all over the world for many years. So I'm not really going to talk about that because this technology is very well known and is used quite extensively in India, both in the automotive market and also in the television industry. What I'm going to concentrate on really today is the second technology, which is a much newer technology called rapid temperature cycling. The company is a full-service provider. We offer complete service to our customers, including design engineering, tooling procurement, equipment, sales and service, and of course design engineering support, processing support. Just one slide on our gas injection business. We sell a complete range of process equipment, including the gas controllers, the nitrogen generators and the nitrogen compressors. But an important part of the business is the design engineering, where we make sure that the parts are designed correctly for the process. Okay, so what we're going to talk about today is a new technology that we are calling rapid temperature cycling. And this is a technology that has really only been commercially available for about 24 months. This is the only text slide that I've really got. But it explains the background to what this process is. It is an injection moulding technology, and in the injection moulding process, when we inject a hot polymer melt into the relatively cold tool, as soon as the polymer comes in contact with the steel of the tool, we get an instantaneous skin layer forming of frozen or highly viscous material. Now this is basically the physics of normal injection moulding, but it has a number of consequences that are less than ideal. Now if we can heat the surface of the mould up to basically above the glass transition temperature of an amorphous polymer or nearer to the melting point of a semi-crystalline polymer, we can achieve a whole range of benefits. These are the benefits that are achievable with this process technology. The first one is elimination of all visible weld lines. So this means that we don't need to paint the part. Actually, the weld lines are still there, but because we have a resin-rich surface, they're actually below the surface of the polymer. We also can achieve a very high gloss surface. Even with materials that are not designed to be high gloss, we can achieve a very high gloss surface finish. We can eliminate silver streaks, which are formed when we have a structural foam material. So if you add a blowing agent to foam the material, normally you have to sand the moulding down and then paint it. Well, again, we can achieve a Class A surface finish without the need for painting. We can achieve excellent replication of the mould surface. So if we have a textured surface, we can pick up that texture much better. Again, because we're retarding the freezing of the polymer to allow the material to go into the peaks and troughs of the grain surface. We have improved optical properties, less birefringence and a more uniform refractive index when we're producing lenses. And what I believe is one of the most important parts is that we can lower the injection pressure by up to 40%. Now this has dramatic consequences with regard to downsizing a wall section. We can downsize the wall sections of the part and still fill at reasonable mold filling pressures. And this means that we can lightweight your parts, and this is very, very important for the automotive industry. If we can downsize our wall section, then of course we can also reduce our cycle time as well. So this technology has been totally driven by the global LCD television producers because they don't want to paint. When you have a plastic moulding and you have to take it away and paint it, then it's a post-moulding operation, it's expensive, it's not friendly to the environment, and you can have scrap rates of anything up to 30%. So the holy grail for the television industry for years has been to find a process where they can mould the parts and take them out of the injection mould straight into the box onto the assembly line. And this process enables them to do this. And because of that, this process has been totally driven globally by the television producers. There's currently, we estimate, around about 450 systems in the world only making LCD TVs. And the process, as I say, involves rapidly heating, and this can be anything from about 6 seconds to 20 seconds, the surface of the mould. It's a misconception that you need a hot mould tool in injection moulding. What you need is a hot surface of the mould as you inject the polymer. Then you want to pull the heat out of that material as quickly as possible, so you want to cool the mould down as quickly as possible. And we do that, basically we heat the surface of the mould by putting dry steam through the cooling channels, followed by cooling water with a high flow rate to achieve our turbulent flow. Why use steam? Well, basically steam contains a huge amount of energy. You don't have to look at all this scientific data. This slide is much more informative. If we take 1 kilogram of water at 100 Celsius, then it contains basically around 420 kilojoules of energy. If we turn that water into steam, because of the latent heat of vaporization, we actually can have steam at the same temperature, but it contains almost 6 times the amount of energy. So steam is a wonderful heating medium if you can control it properly. We use our RTC controller with a steam pressure of 10 bar, and at 10 bar the steam has a temperature of 180 Celsius. So when we put the steam in, we can rapidly heat the surface of the mould up. RTC consists of 3 principal elements. The mould tool has to be designed for the process. You can't apply this technology to an existing mould, so you have to design the mould tool for the process. So we need a special mould tool, we need to have a steam generation system, and we need the controller that we fix to the injection molding machine. On the tooling side, what we're trying to do is we're trying to produce a low thermal mass cavity shell, because the more steel you have to heat up, then the more energy you need. So we try and make a cavity shell with a low thermal mass that can save us our energy. We need to use corrosion-resistant steels, typically stainless steel, and the tool is made with conformal channels. And what I mean by that is the channels follow the contour of the mould in 3 dimensions. The mould can be made using various mould making techniques. If it's a relatively small mould, then we can use either laser sintering or selective laser melting, or even metal spraying to make the mould. But when we're talking about large televisions, then we use conventional CNC machining techniques, splitting the mould cavity into 2 parts, machining both sides and then bringing it back together. This is an example of an automotive application, and you can see where we have the conformal channels basically following the shape of the mould tool. Again, this is showing the how the construction of the mould is. We have our stainless steel cavity shell, and in this particular mould we have an aluminium conformal channel base, and then we insulate it with a resin plate. This is very important because we don't want to heat the whole mould bolster, we just want to basically heat the cavity plate. We work with a number of mould makers that have got a lot of expertise in making these kinds of moulds. This company, although the name is Hong Kong and China Moulds, it's actually a British-owned company. 3 of the UK's very well-known tool makers have set up 2 tool making factories in China, and we use this company extensively for making our moulds. But basically, any mould maker can make these tools if they know basically how the process works. On the steam generation side, we have what we call a dedicated steam generator, a DSG. And if we're running only 1, 2 or 3 machines, we can actually have an electric steam generator. When we're looking at the big television factories where we might be running 5, 10, 20 machines, then we normally use oil or gas-fired boiler systems. This is the steam controller itself, and this is a machine that's actually attached to the injection mould and interface with the injection molding machine. This is the 3rd generation of machine. Here you can see the various inlets and outlets. This machine actually has to go behind the injection molding machine, and therefore we have a handheld control panel, so the operator can be at the front of the molding machine and still control the process variables that he needs to control on the injection molding machine itself. Now, which steam controller? We have 3 models, so the obvious question is, well, which size of controller do I need? Well, Unlike injection molding,